Hi, I'm Han Lingren from Tsinghua University, and in this video, we are going to talk about a distance sensitivity oracle in subcubic preprocessing time. So let me define the problem first. In a distance sensitivity oracle, you are given a directed graph G, and you want to preprocess it into a data structure that supports the following kind of queries. In each query, you are given three vertices u, v, and x, and you want to find the shortest path from u to v that does not go through x. For example, this is a valid query, and the answer to this query is the blue path, which is the shortest path from u to v in the graph with x removed. The problem of building DSOs is a natural and well-studied problem in graph algorithms. Let me review some previous work. The naive algorithm for computing a DSO is simply to precompute the answers for every possible query. Since there are only n³ possible queries, our naive DSO has base complexity n³ and constant query time. Demetrescu et al. Constructed a DSO with base complexity n² and constant query time. However, their DSO requires mn² plus n³ log n preprocessing time. In follow-up works, Bernstein and Karger improved the preprocessing time to mn. The uphill shortest path problem is conjectured to require mn time, and the uphill shortest path problem is easier than building a DSO. Therefore, the mn preprocessing time is optimal in this sense. However, if we assume the graph has small integer edge weights, then uphill shortest path can be solved in subcubic time by using fast matrix multiplication algorithm. So there is a natural question. Under the same assumption, can we build a DSO also in subcubic time using fast matrix multiplication algorithms? There are some previous work in this direction. The first problem would be, can we achieve subcubic preprocessing time? And this was answered affirmatively by a paper of Weyman and Euster. They gave a DSO with preprocessing time O n to 1 minus alpha plus omega and query time O n to 1 plus alpha. Here, omega is the matrix multiplication exponent, and alpha is a parameter between 0 and 1 of your choice. Notice that the query time for this DSO is superlinear, so a natural question is, can we achieve sublinear query time? Brandoni and Williams shows the answer is yes. And in particular, they gave a DSO with preprocessing time n to omega plus 1/2 plus n to omega plus alpha times 4 minus omega, and query time O n to 1 minus alpha. Again, this alpha is a parameter between 0 and 1. For suitably chosen alpha, the preprocessing time is subcubic and the query time is sublinear. However, we still want as fast a query time as we can. So can we achieve near constant query time? This problem was addressed by a recent work by Chechik and Cohen, and they gave a DSO with preprocessing time O n to 2.8729 and query time polylog n. Now we can introduce our main result. We show how to build a DSO with preprocessing time O n to 2.7233 and constant query time. Moreover, our algorithm is much simpler than the algorithm of Chechik and Cohen. In the paper, we assume the graph has integer edge weights no more than w. However, to make things simple, we will assume in this talk that the graph is unweighted, that is, w equals to 1. We will also assume that shortest paths are unique. However, let me remind you that the unique shortest path assumption is actually dangerous in our setting. This is because in an unweighted graph, the shortest paths are typically not unique, and if we want to ensure unique shortest path, we need to perturb the edge weights by small random amounts, and after that, the graph is no longer unweighted. and we cannot use the subcubic APSP algorithm on these graphs. However, we will still assume the shortest paths are unique in this talk. So, let me give a bird's eye view of our algorithm. Instead of building a DSO in one shot, we focus on a weaker concept which is called r-truncated DSOs. It basically means a DSO that returns the correct answer when the answer is at most r and returns r otherwise. So we have two cases. First, if r is a small value, then we can build an r-truncated DSO by standard techniques of random sampling. And second, if r is large, our idea is to boost an r-truncated DSO to a 3/2 r-truncated DSO. So what does our algorithm look like? We first invoke case 1 to build an r-truncated DSO for some appropriately chosen r. Then we iteratively apply case 2 to this DSO. In the first iteration, we boost this r-truncated DSO to a 3/2 r-truncated DSO. In the second iteration, we boost the 3/2 r-truncated DSO to a 3/2 squared r-truncated DSO, and so on. After log n iterations, it becomes an n-truncated DSO, which is a normal DSO. So let me introduce the algorithm where r is small. Recall that we only care about shortest path with at most r vertices. Let's imagine that we randomly remove 1/r fraction of vertices, which means that for every vertex, we remove it independently with probability 1/r. Then we compute the outpair shortest path in the rest graph. Let's consider a query UVX. Here and after, we will use the notation UVX to denote a query which asks the shortest path from U to V that does not go through X. So here is a query, and the green path is the answer to this query. We say a sample preserves this query if first X is removed from the sample, and second, the green path is preserved in the sample. We can see that if a sample preserves the query, then the shortest path from U to V in the remaining graph of this sample is exactly the answer to this query. So what is the probability that a random sample preserves a particular query? First, we need that X is removed, and second, we need that every vertex in the green path are preserved. Notice that the green path has at most r vertices, so the probability is at least 1/r times 1 minus 1/r raised to the r's power. After some calculations, it's at least 1/4r. It means that if we take (or) independent samples, then with high probability every query is preserved by some sample. Here is an illustration. First, let's say we take 3 samples, and in each sample, we will randomly remove some vertices and their incident edges. And then we compute the outpair shortest path inside each sample. Now, assume we are given a query UVX, and we can see that the second sample preserves the query UVX. So if we ask the distance from U to V in the second sample, it is exactly the answer to this query. Now, let's analyze the time complexity of this case. Recall that we took (or) samples and compute the outpair shortest path of each sample. In the outpair shortest path computation, we only care about distances at most r, and this can be done in time n to omega times r to 3 minus omega. The preprocessing time is (or) times the above time bound. The query time is polylog n. To see this, we note that for every failure x, there are only polylog n samples that does not contain x. So the query algorithm is very simple. We iterate through every sample that does not contain x, and we find the shortest path from U to V in that sample. At last, we out the path with the minimum length that we found, and this is with high probability the answer to this query. Now let me introduce the second case. Assuming we have an r-truncated DSO, we want to boost it to a 3/2 r-truncated DSO. The idea is also standard. We sample tilde O n over r vertices denoted as H, which means heating set or bridging set. On a query UVX, what we do is, first we enumerate every small h in this heating set, and we use the old oracle to compute the shortest path from U to H not going through X, and from H to V not going through X. We add these two numbers together and we return the minimum of the answers over all H. So for example, there is a query UVX and our algorithm simply enumerates H. Why is this correct? Let's consider a query UVX. Without loss of generality, we may assume its answer is greater than R, but no more than 3/2 R. This is because if the answer is at most R, then we can answer this query by the old DSO, and if the answer is greater than 3/2 R, we simply don't care. We claim that if H hits the middle 1/3 portion of the answer path, then we can answer this query correctly. So imagine that this U to V path depicted in the slides is the shortest path from U to V not going through X, and its middle 1/3 portion is the blue portion. If there is small h in this middle 1/3 portion, then we can see the distance between U to H is at most R, and the distance between H to V is also at most R. Both of them are preserved in the r-truncated DSO. Therefore, our 3/2 r-truncated DSO will give the correct answer on this query. So if we randomly sample tilde O n over r vertices in H, then with high probability for every valid query UVX, this heating set actually hits the middle 1/3 portion of the answer path corresponding to that query. So in this case, the answer to every query is correct. However, there is still an issue, that is our query time. Even assuming our r-truncated DSO has constant query time, the query time of our 3/2 r-truncated DSO is somewhat high, is tilde O n over r. However, we want constant query time. So here comes a magic lemma, which says that given an r-truncated DSO with preprocessing time p and query time q, we can construct an r-truncated DSO with preprocessing time p plus tilde O n squared q and constant query time. With this lemma, we can finish our boosting theorem from r-truncated DSO to 3/2 r-truncated DSO. First, we have an r-truncated DSO with preprocessing time p and constant query time. We use the bridging set to construct a 3/2 r-truncated DSO with preprocessing time p and query time tilde O n over r. Then using this lemma, we can boost it to a 3/2 r-truncated DSO with preprocessing time p plus tilde O n cube over r and constant query time. So what we get is, we can boost an r-truncated DSO to a 3/2 r-truncated DSO in tilde O n cube over r time. Let's put the pieces together and see what the final algorithm does. First, we can construct an r-truncated DSO in n to omega r to 4 minus omega times. Second, given an r-truncated DSO, we can boost it to a 3/2 r-truncated DSO in n cube over r times. So our algorithm starts by invoking case 1 for an appropriately chosen r, which takes n to omega r to 4 minus omega times, and we build an r-truncated DSO. Then we invoke case 2, which takes n cube over r times to boost it to a 3/2 r-truncated DSO. We invoke case 2 again, and we get a 9/4 r-truncated DSO, and so on. After log n invocations of case 2, we get an n-truncated DSO, which is what we want. And we can see that the running time is dominated by the first two steps, that is the invocation of case 1 and the first invocation of case 2. After some computation and choosing the best R, you can see the time complexity is n/2.7613. Using some rectangular matrix multiplication algorithm, we can improve it to n/2.7233. It may seem that there's some sort of magic behind this lemma, so let me demystify it in this slide. The lemma says that given an r-truncated DSO with preprocessing time p and query time q, we can construct an r-truncated DSO with preprocessing time p plus O n squared q and constant query time. For ease of presentation, let's just consider normal DSOs instead of r-truncated DSOs. Our proof strategy is very simple. We just do what Bernstein and Karger did. Recall that the Bernstein-Karger paper constructed a DSO with (O)mn preprocessing time and constant query time. We can abstract their algorithm as follows. Their first step is to compute (O)n squared DSO queries, and these queries are somewhat structured, so they can somehow answer these queries in (O)mn time. After that, they showed how to build a DSO from the answers of these DSO queries. And what do? We simply replace the second step by answering these queries by the slower DSO. So we can see that our preprocessing algorithm for the faster DSO just invokes the preprocessing algorithm for slower DSO and asks n squared DSO queries to the slower DSO, so its preprocessing time is p plus O n squared q, and the query time is constant by Bernstein and Karger's construction. Okay, I also want to share with you how we break ties, that is, how we deal with non-unique shortest paths. Recall that in an unweighted graph, the shortest paths are usually not unique, and this is annoying. Our solution is as follows. First, we assign a distinct index to every edge. For example, this path represents a portion of the input graph, and we assign a distinct index to every edge. Then we define the bottleneck of a path as the smallest index of any edge on the path. As an example, the bottleneck of this path is 3. Which is labeled by the yellow edge. We define WUV as the largest possible bottleneck of any shortest path from U to V. So there may be many different shortest paths from U to V, and we pick the shortest path with the largest bottleneck. We denote WUV as the bottleneck of this shortest path. Duan and Petty showed that the values WUV for every pair of UV can be computed in subcubic time, and this problem is called the all-pairs bottleneck shortest path problem. In contrast, if we randomly perturb the edge weights by small values, it's not known how to compute the all-pair shortest path in subcubic time. Now, let's define a tie-breaking method. For every UV, we want to define a specific shortest path as the shortest path from U to V. Let U prime to V prime be the edge with index WUV. The shortest path from U to V is recursively defined as the concatenation of, first, the shortest path from U to U prime, and second, the edge U prime to V prime. Third, the shortest path from V prime to V. And as we solve above, the shortest path trace can actually be computed in n/2.687 time. Actually, it can be computed in n squared time given all the values WUV. Here is an example. If we have two vertices U and V, and we want to compute the shortest path from U to V, We first compute the edge weight index WUV, and let's say it's U prime to V prime. Then we recursively find the shortest path from U to U prime. To do this, we also find the edge with index WU prime, and we recursively find this shortest path on the left, recursively find the shortest path on the right, and concatenate them to form the shortest path from U to U prime. And for the shortest path from V prime to V, we use the same recursion. So we can find the designated shortest path from U to V by this algorithm. And this definition has two desirable properties. Let pi be a shortest path, such as the depicted path from U to V in the slide. First, subpaths of pi are still shortest paths. What does this mean? It means that if we are given two intermediate vertices on the path pi, and we compute the shortest path between these two intermediate vertices using the above algorithm, then we can find that the shortest path we find is exactly the portion of pi between these two vertices. The second property is that let E be any edge not in pi, then pi is still a shortest path in G minus E. That is, if we use the same algorithm to find the shortest path from U to V in the graph G minus E, then it will turn out to be equal to pi. And these are very desirable properties for a type-breaking method for dealing with non-unique shortest paths. The proofs can be seen in the archive version of this paper. Let me conclude with some open questions. I think the most important open question is, what is the exact complexity of preprocessing a DSO? For example, can we preprocess a DSO in ESA.2.5 3 times, which is the current best time bound for APSP? Also, for undirected graphs, can we preprocess a DSO in ESA.2 omega time? This is also the time bound for undirected graph APSP. There are some other open questions that I find interesting. First, the size of our DSO is only ESA squared, but the preprocessing algorithm requires superquadratic space. This happens in step 1 when you are using random sampling to build an r-truncated DSO. You actually need to make r samples, and in each sample you need to store an APSP result which takes n squared space. So the total space of the preprocessing algorithm is r times n squared. It seems open to improve the space requirement to simply n squared. And second, can we handle negative edge weights? The DSO in this paper cannot handle negative edge weights due to some subtle point in Bernstein and Karger's algorithm. Let me report some new progress on DSOs. In an ongoing work, we show we can build a DSO in ESA.2 C plus omega over 2 preprocessing time. And the new ingredient we use is the symbolic computational methods from a paper of Vandenbrand and Saranurak in Fox 19. That's all. Thank you.